Hello, I'm Chikami Nabago, and this is my presentation for Lab 3 on a black hole. In terms of our introduction, the purpose of this lab is to find the mass of a black hole by analyzing a star's orbit, and we'll use this information to find the initial velocity that the ship must have when it leaves the surface of the planet to fly around the black hole without crashing on the planet or the black hole. Fundamental principles that we're going to use is the Newton's second law of momentum principle, F net equals mass times acceleration, and its derivations, and Newton's universal law of gravitation, and the lab result is shown there as well.
So in terms of the fundamental physics ideas that drive this experiment, like stated previously, we have universal gravitation, Newton's second law / the momentum principle. I also made a point to show the perpendicular and parallel components, which is relevant because of the circular motion that we're studying today. And perpendicular shows change in direction, while the parallel component shows the motion of the object. And we'll also use the velocity update formula and the position update formula. And we're assuming that F net is only the gravitational force because that's the only force acting on our system at the moment. And we have what mass will equal when we move the equations around. So here's some reasoning to back up some of my choices in terms of like the fundamental laws that I'm using. Since this is in space, the only forces acting on the star are the gravity of the black hole, and the only forces acting on the spaceship are gravity from the black hole and from the planet. So F net equals gravity. Universal gravitation is non-constant, so average velocity in this case will be replaced by the final velocity in our kinematic equations. F net parallel is in the same direction as motion, so the object is speeding up, and changing the F net perpendicular changes the direction of the object. In this scenario is our black hole, and the surroundings are the star. So our initial objective of finding the mass, we have to establish initial conditions. The mass of the star is 2 × 10⁻30 kilograms. The time for the first observation data point, we defaulted to time equaling 0. Delta T is 1 day equaling 86,400 seconds, and our gravitational constant is stated there. So here's the code showcasing how we're going to find the mass applying Newton's second law through the Python code. So in the red, we have F net, which is simply the change of momentum over time. And then the parallel component of F net is shown through us finding P hat first, and then using that to find the F net parallel through P initial divided by the magnitude of the initial momentum. And then we just subtract the parallel component from F net to give us the perpendicular component, because F net is F perpendicular plus F parallel. Here we have the code that shows us how we found the mass of the black hole, which was basically our kinematic equation in terms of in it being rearranged using the magnitude of the net force and the magnitude of the star's position. From that, our code computed the mass of the black hole, which was 7.391 times 10⁻33 kilograms. The magnitude of F net and the magnitude of F net parallel and perpendicular is stated below as well.
So here's the code in terms of the initial conditions that was wrote up to find the initial velocity of the spaceship. We have our system being the spaceship and our surrounding being the planet and the black hole. So we just lined up what G is, what the mass of the planet is, mass of the ship, planet's velocity, and things of that nature, just to start us off. Next step to finding the initial velocity of the spaceship is to calculate net force. First, we're going to find the magnitude of the position. Then we'll find r hat, the unit vector of this position vector. And then we will find F gravity using the universal gravitational law. And then from that, we can find the magnitude of the ship to the black hole. The code computed that the initial velocity of the spaceship would be the vector negative 5.26 times 10⁶, 6.90 times 10⁶, 0. The closest distance between the spaceship and black hole would be 1.614 times 10 meters. Times 10 to the power of 10 meters. Sources of error include the fact that I might have ran the program for a shorter amount of time than I should have. So if I ran it for a longer time, I could have a more accurate average mass. And then also I might have had the incorrect initial velocity because I used the guess and check method, and that the time interval could have been too short. What does it mean question of how are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? F parallel is net force parallel to the direction of motion equals the change of magnitude over the change in time times P hat. F perpendicular is net force perpendicular to the direction of motion. Net force equals the change of momentum over change in time, which equals mass times acceleration, and that equals all the forces acting on a system. The rate of change of momentum equals the final momentum minus the initial momentum. So that's different from the net force. And momentum equals mass times velocity. It is easier to find the change of momentum than it is to find the net force. Question. To predict the motion of the system, the computational model must account for gravitational interactions, mass, distance, orbital mechanics, relativistic effects, tidal forces, and time evolution. Gravity is the dominant force, with each object exerting an influence on the others. The black hole likely has the strongest gravitational pull, significantly affecting the star, planet, and moon. So in summary, this model would have to account for way more complex things that are happening in the real world compared to our initial theoretical model.